Moving on to section 2 of chapter 7, we're now going to talk about measuring the quality of a survey and what makes a good survey. So the first thing I want to ask, or the first thing to think about is, how do you know if a survey is representative of the population? And so in general, statisticians don't measure the way that they measure how representative the survey is by looking at the estimation method that is used instead of just looking at the outcome. The outcome might be very promising, the outcome might be really bad. That's not really the main focus, but what we want to look at is the estimation method representative, or is the estimation method set up in a way that can yield accurate and non-biased results. And so the goal for a good estimation method would be for the survey method to be accurate and to be precise. Okay, so accurate, the statistical definition for accurate would suggest that the method measures what it's intended to. So it correctly estimates the population parameter. An important note about accuracy. Accuracy is measured in terms of the bias. If there's no bias, then that means that the method is accurate, vice versa. And then precise, the definition for precise would be that if the method is repeated, the estimates should be consistent. So precision is determined whether or not the estimates are consistent with each other. An important note about precision. Precision is measured by a number called the standard error. The standard error, we'll talk about it in more detail later this chapter, but what I need you to understand right now, that a smaller standard error indicates better precision. So before I move on, I do want to provide a little visual of what it means to be accurate and precise. So let's go back to accuracy. So a method is accurate if it measures what it intends to. So it correctly estimates the population parameter. So let's say that the goal is to be able to hit the bull's eye. So imagine these are my targets. And the goal is to hit the bull's eye. So it's possible that I can shoot, or I can throw my dart and it lands there, here, and here. So overall, my darts are pretty accurate. They're close to the bull's eye. But in this case, they're not really precise because they're kind of spread everywhere. So they're close to the target, but they're not precise. So this is an example where it's accurate. Well, let me rewrite that. So accurate, but not precise. Okay. Now let's look at an example where it's precise but not accurate. So precise, a method is precise if the estimates are consistent. And so it's possible that I threw my dart, it lands here, threw another one, lands right there, another one, another one, another one. So overall, they're pretty consistent with each other. They all land on that bottom right corner, but they're not close to the target or to the bull's eye. So in this case right here, we have a method that is precise but not accurate. So finally, let's look at one that is accurate and also precise at the same time. So here we can assume that if it's accurate, it's going to be close to the bullseye. If it's precise, it's going to all be close to each other. So perhaps something that looks like this. So it's accurate because it measures what it's supposed to, so it's close to the bullseye. And it's precise because each of them are consistent with each other. So accurate and precise would be this bottom one. So I hope this provides a visual and understanding what it means to be accurate and precise. Okay, so Now I'm going to start talking about some behaviors of estimators, or some behaviors about the statistics. So the first behavior is that statistics vary from sample to sample. So it might be true that, let's say, 25% of my class prefer the color red, but another Math 1150 class might have a 50% proportion that prefer the color red. Might have another Math 1150 class where all of them prefer the color red. And so statistics vary from sample to sample. It's not going to be one same number each time. Some remarks about this behavior. The population proportion. So let's say that the proportion of all math, or the proportion that, so let's say that the population were all Math 1150 students, and we found that 25% prefer the color red. Then that population proportion will always stay the same no matter how many different samples we take. So the sample can change, or the sample statistic can change, but the proportion, the population proportion will always remain the same. The second remark, again, the sample proportion p hat can change from sample to sample. The reason why we're talking about the proportion is because, as I've mentioned, this chapter focuses on the proportion. We're not really talking about the mean or the standard deviation in this chapter. This sample proportion p hat has a probability distribution, which we'll refer to as the sampling distribution. Some other remarks about behavior 1. The bias is measured as the distance between the mean value of p hat and the population proportion p. And so the mean value of p hat has this notation right here. So mu sub p hat. This is going to be used to indicate the mean value of p hat. And then the population proportion p. So if there is no bias, then the difference should be 0. The smaller the number, the more, or the less bias there is. The bigger the number, the more bias there is. Final remark, the standard deviation of the sampling distribution is going to be known as the standard error. Again, we'll talk about this in more details in a few slides here. Now the second behavior. So the second behavior is that the size of the population doesn't affect the precision. So the remark about behavior 2 is that precision is an estimator, so it does not depend on the population size, it only depends on the sample size. Finally, the last behavior is that large samples produce more precise estimators. So as we have seen, in chapter 5, we talked about the law of large numbers. So the more repetitions there were, the closer the two probabilities converged to each other, and so the more precise it became. So the same idea here. The larger the samples, the more samples that you take, the more consistent they will be. So a remark about behavior 3, larger samples have a smaller standard error because they're more precise. So now I'm going to talk specifically about the bias and standard error for a simple random sampling. So far I've only talked about bias and standard error overall, but now what does it mean in terms of being a simple random sample? So for simple random sampling, the following will be true. Number 1, the bias is always assumed to be 0 because a simple random sampling is without replacement and is also equally likely and random, ruling out all chances of being biased. So that's to say that the mean value of p hat, or mu p hat, minus the population proportion p will be 0. Again, just in case you're not familiar with the notation, this mean of p hat and mu p hat right here is just the mean of the statistic p hat. So lucky for all of us, we're assuming that all of our samples are simple random samples, and so the mean or the bias will always be 0. And then the standard error. Now finally talking about what the standard error is. So again, the standard error is a measure of precision. It's telling us how consistent our samples are. So the standard error has this formula right here, only if the next three conditions are true. So in general, standard error should be the square root of p times the quantity 1 minus p all over n. And n in this case is the sample size. So the first condition that must be true is that the population proportion is known. So if we look at the formula has p in it. So if p is not known, we can't use this formula. So that's the first condition, is that p, the population proportion, must be known. Condition 2, the sample must be random, with or without replacement. But again, since we're assuming that the rest of our samples are simple random sampling, then we don't really need to worry about this. The final condition, if sampling is done without replacement, then the population needs to be at least 10 times bigger than the sample size. So these three conditions must be true in order to calculate the standard error using this formula. So sometimes we might run into an example where we don't know p, or p is not given to us. So the population proportion is unknown to us. But that's not too big of a deal, because what we can do is estimate the standard error using the sample proportion. So if we don't know the population proportion, we can always rely on the sample proportion to estimate the standard error. And so anytime that the population proportion is not given or is unknown, then we can use this formula right here. So this is going to be the standard error estimated, which is going to be the same thing, except now we're replacing p, the population proportion, with p hat, the sample proportion. So again, this is only used if the population proportion is unknown or not given to us. Other than that, the one that we should be using would be this formula right here. So I hope you make a clear distinction between these two and the criteria for using the standard error estimated formula. So in the next section here, we'll talk about the central limit theorem for sample proportions. This is going to be a very quick section, but a very hard section. So I'm going to go through one really big example with all of you, and then we'll cover more examples if needed in the WebEx lecture on Friday.